Hello, everybody. Welcome to my talk, Proven Schema Designs and Best Practices. My name is Jeff. I'm a full-stack engineer with almost 9 years experience using GraphQL. And I recently joined the Guild at the beginning of this year, and I work on the Hive console team. I field technical GraphQL questions daily. These might be general questions or specific to our Hive products. And prior to the Guild, I worked as a site reliability engineer at a fintech named Acorns, where I wrote and managed their GraphQL gateway. I also ran an operational readiness review process and regularly participated in architectural design reviews. So I guess I'm just trying to say that schema design is very near and dear to my heart. So like I had mentioned, I work on Hive these days, and Hive is a full suite of GraphQL tools and services, and this includes TypeScript Gateway that we just released a version 2 of, a new Rust router, and Hive Console, like I said, that I work on, is our schema registry. So it helps you explore, manage, and publish your schemas and more. Everything we do at the Guild is open source, MIT license, so you can even self-host Hive Console if there's no vendor lock-in or anything like that. And if any of this sounds interesting to you, or if you're looking for a way to contribute to the GraphQL community ecosystem, the Guild would be thrilled to collaborate with you. So you can always reach us through our website. I'm also an avid gardener, so you'll see many of my examples are plant-based. Here, I just want to say that if you take one thing away from this talk, I hope it's that you can and should future-proof your schemas as much as possible, but it's okay for the schema not to be perfect. Products change, requirements change, there will be chaos. But we can tend to our schemas, we can encourage them to grow and evolve organically, and it's much like a garden. So with that, let's get into why and how we tend to our schemas. I'll be covering some goals we should have when designing our schemas, some battle-tested patterns for each of these goals to help avoid pitfalls, and finally we'll cover some practical ways in which we can approach designing our schema. The first goal is for your schema to be easy to change over time. As I mentioned, entropy is constant. So if you anticipate and prepare for change, then you can more easily adapt your schema to fit the needs of your consumers. And how do we do this? Well, it may be unintuitive, but keeping your field arguments concise, your fields inflexible actually, is one way to keep your schema as a whole more flexible. So we don't overload arguments or input types with a bunch of optional ways of doing things. And by keeping fields more focused, we limit the impact that any one change can have. And if we do need to break things, then the blast radius of that change is much smaller. And also adding a new field is just much easier than modifying an old one. And similarly to the last point, if you try to overload mutations, then it's difficult to migrate them. So not only that, but it can also hurt performance. And this is because it requires your resolver to do many things before returning instead of just the one. So it's best to keep your mutations focused on a specific task. Here we have two examples of user types, but on the left is one that has only what your consumer needs. On the right, it might be everything you know about a user. It should be obvious that the left is much easier to maintain. So here again, I'm trying to get across that you shouldn't expose every single field with every single bit of data that you have all the time. I've seen a lot of backend engineers expose data unnecessarily, and that's because they think maybe it could be useful, only to find out that these fields go unused, or even worse, if the format of the data ends up not being right because they didn't have a user story to work off of. Tooling such as GraphQL Hive can also help. We offer a feature called conditional breaking changes, and that checks for usage data on breaking changes. And if the portion of the schema that broke is not used, then the change is allowed. Otherwise, the change is still flagged as breaking. And this lets you safely migrate your schema and eliminates the need to manually check usage on breaking changes. Another goal is that traversing the graph should be quick with as few hops as possible. And this helps the API be more client-friendly, reduces strain on your system from too many lookups or connections. And if you want to empower your consumers, or if you want to empower your consumers, to use your data, not force them to solve a problem or do hours of research or whatever in order to find what they're looking for. So make data accessible, and it'll be efficient for both your servers and your consumers. And a proven way of doing this, that I assume all of you already know actually, is to use a node interface for every single entity type. So it's also fine to opt into not doing this pattern. So long as you expose a way to access related types, that's absolutely fine. Just forcing your clients to make multiple calls is obviously not ideal. Another way to make your API more accessible is to better support partial results. Returning partial data can dramatically improve a user's experience. And for example, if your system has a partial outage, you can at least return something. And keeping root fields nullable ensures that any one field can't break the entire client operation. Benji actually had a talk on nullability the other day that has some really exciting changes that will basically make this entire point moot. And the next goal is to be safe and secure. So to have a secure schema means to avoid leaking sensitive information, but also not being vulnerable to attacks. One major vulnerability of vanilla GraphQL is denial of service attacks. And a note on that, there's really no substitution for like setting reasonable request timeouts. A lot of times people might forget those. But tooling that restricts the size of your requests or rate limits requests is also necessary for preventing DDoS attacks. Tooling like GraphQL Armor, hopefully you're all familiar with that. And there's also a few ways of designing your schema to limit attacks by limiting response sizes. So this schema on the left shows the relay pagination spec. And using pagination limits the amount of load from any one field. But there's other pagination specs out there. Again, use whatever works best for you. The important thing is that you use pagination to reduce the potential for DDoS attacks and to increase the responsiveness of your API. And this is important even if you're using rate limiting, by the way. And I guess, again, one more small exception is that if you know your data is guaranteed to have a small upper bound, like say there's only 10 plants that existed in the world, then you can get away with a simple array. Like don't add that complexity if you don't have to. You can see the vast difference of those schemas. And don't place binary files or other large responses in your schema. I've sometimes seen base64 encoded things in the schema. Generally, leverage CDNs or other purpose-built solutions that are meant for dealing with these large files. Another goal is for your schema to expose clear ways to interact with it. So specifically, I'm talking about mutations or subscriptions. You must give your clients the data that they need to do their job. And this may seem like an obvious statement, but many times edge cases are forgotten or ignored. Edge cases like errors. So placing your expected errors in the schema is incredibly valuable for consumers of your API. And this lets your API consumers know what can go wrong, potentially how to fix those issues, and more. This is sometimes called typed errors or errors as data, sometimes expected errors. Whatever you call it, just make sure to add meaningful fields. And that can really help your client show information to the users instead of something generic, just like something went wrong that we hate seeing everywhere. And don't move every single network failure into your schema. Those errors are potentially numerous and honestly meaningless to your consumers. And those should be thrown and masked in production to avoid leaking any sensitive information and to avoid forcing your clients to handle these cases. There are a few convenient ways to expose errors in your schema. The first would be as a union of both the success and the error results. This adds a minimal amount of types to your schema, but relies on convention to separate out the different types. The other is to create a response type that has both a success and error field. And one is convention, the other is codified. But otherwise, there isn't really much difference, and I think both are fine. And consistency is really important. Consistency is promoted by using patterns, and patterns make it easier for your team to develop because they know how to do things. And this applies both when developing your schema and consuming your schema. And if everything is slightly different, then it's much harder to navigate because nothing is intuitive. So, like I said, consistency comes from implementing all of these things all the time. And some tools like linting can help, particularly when implementing linting rules in something like a schema registry or some central service, so that it affects every single schema if you're using federation, every single subgraph. And one recommendation here is that this central location should enforce patterns, but not stylistic choices in your registry or wherever else. Many times teams have their own stylistic preferences, and they can implement linting in their own service for that. I think that kind of information, that kind of formatting isn't really a concern for anyone outside of that project. And the last goal we have is to be descriptive and unambiguous. So this means that your entities are accurately reflected in the schema using shared language. What does shared language mean? Simply put, it's that your types and fields are named well, so there's no confusion between them and no data redundancy. So a shared language is just like what everybody calls it. And that's still a pretty broad statement, so let's look at some design approaches and how they can be used to create a descriptive and unambiguous schema. Keep in mind that most systems are not purely one way or another, but there's a few approaches that are most common or most successful from my experience. The first is inside-out design. So this focuses on exposing internal structures and is typically the easiest but least optimized. Easiest for developers, that is. It could result in a very CRUD-like API. And the next is outside-in design, which focuses on client needs first. The types may be totally abstracted from the underlying implementation, but that could be fine. The last I'm going to discuss is domain-driven design. Domain-driven design focuses on your objects, their attributes, and relationships, and requires the most familiarity with your product. Note that to design anything, you should always start with a set of user stories. So let's look at inside-out design first. Here we start with user stories that define the data fields, interactions, implement the data types and relationships as a database, and make sure that it satisfies those stories. And then you just simply map those to GraphQL types. Here's an example user story for a feature that I've been working on lately. And from this, we can extract the nouns, which then could represent the attributes or other data types. So action verbs may also hint at data requirements. Here the phrase can author a schema proposal hints at the need to track who created the schema proposal. Inside-out design comes naturally to developers, like I had said. Typically those who are, work with databases, maybe not so much just solely front-end developers. But you design the database to meet the requirements and then convert that one-to-one to the type. External references like the target ID and user ID that you see on the left are exposed as additional fields on your type, like target or user. Pretty simple. And it makes sense to use inside-out design if you're given an existing database and need to get an API up and running immediately, or if your application only calls for simple CRUD calls, why overcomplicate things? Or if you're rapidly prototyping something because inside-out design helps you focus your time and energy elsewhere. Also, any change to the data map is essentially one-to-one because you're changing your data, you're changing your schema, and so that's a fixed cost when prototyping, and that can come in handy. How about outside-in design? So again, we start with user stories, but obviously instead of a database, we build a UI UX to meet the requirements. And typically based on the proximity or hierarchy, we extract types and fields to build your entities. And for the purpose of time, I'm going to skip the user story. We can just focus on the UI. I mentioned I'm a gardener. Well, I'm from California. We have a really great tool called Calscape, and it's a catalog of native plants, and that's what I'm using for this example. So ignoring pagination for simplicity at the moment, we can see that this UI has some very clear requirements. So very simply, we look at all the different components and determine what belongs to the same entity. In this case, everything is referencing a single plant. So it makes sense to add this to a plant type, as you see. We have a scientific name, and available nurseries, as well as photos. When would you use this? So if the company you work for is very design focused, has a very strong design team, again, like piggyback off that work, make life easier on yourself. And if you have a single client consuming from your schema, then you may want to build your API around that one use case, and then you can revisit it later. And like if the schema turns out to be confusing as a result of this, like of course you can migrate it, you can change it. And lastly, if there's an odd feature that has like very strict performance requirements that you can't quite get to fit with the other types, this is kind of an edge case, and usually it's just based on like the amount of time you have to develop. But you might consider just creating a new type, basing it on the UI, and moving on with your life. So basically, if there's a significant performance benefit for designing the API, go for it, do it. Don't cripple your API for some like esoteric reason. So onto domain-driven design. And domain-driven design is a broad, very complex topic. I mean, there's conferences dedicated to that, just that. But at its heart, it's based on some concepts that we use every day without realizing it. So in this, one of the concepts here is bounded context. And this example diagram shows a couple of bounded contexts. But in reality, each of these nodes, which might be mapped to one of our types, has its own bounded context as well. So, and not to overcomplicate things, but there's also a bounded context surrounding everything. And fortunately, the human brain is very good at figuring out the right context. And to me, this is kind of similar to the concept of abstraction, which of course is like a very important one in computer science, and it's a fundamental principle. So you're hopefully all familiar with that. But yeah, just every layer of your context gets more and more specific. And like I mentioned, we do this every day. So when chatting with somebody, the context is determined by your relationship to whoever you're talking to, as well as the conversation up to that point, as well as time, like location, and maybe current political climate. Inside jokes are a result of bounded contexts with your friends, and anyone unfamiliar with that context wouldn't know what you're talking about. So when talking about our schemas, the bounded context will inform your language, and that language becomes your types. And with that out of the way, we see that it's much like many of the other approaches. So we start with user stories, next we define bounded contexts, and this requires a conversation with and domain knowledge. And it's questions like, what other objects exist in your schema? What's the goal of your API? Who is the consumer of your schema? That kind of informs the broader context. And if you can answer those questions, then you can typically determine the entities and prescribe, hopefully, more commonly understood names to them. Or the domain-driven design term is actually ubiquitous language, but we can just avoid that. And iteration is expected here. It's a natural part of domain-driven design. But yeah, contexts are always changing as well. So again, thankfully, GraphQL is built with evolution in mind. All right, let's say that I'm designing a native plant site like what I showed earlier. I've taken the liberty of creating what I believe are the entities based on some user stories I've been provided. And I've divided these into bounded contexts. So this can be as simple as finding similarities between the entities. And let's talk to our product manager and like confirm our user stories. Let's make sure that our list of entities makes sense. So our first user story might be that a user must know how to care for a plant. Seems straightforward. I assumed that to care for a plant requires people and tools, but let's ask a question. So what does it mean to care for a plant? Well, they might respond, to care for a plant means to satisfy its growing conditions like sunlight, water, and soil. Nothing to do with people or tools. So those go away. The next user story is that as a user, I must know what sort of things rely on a plant. So probing deeper, we might find that we want to track which plants a bee, wasp, or butterfly might pollinate, if a bird eats berries off the plant, if a caterpillar eats the leaves. And it turns out that each of these have unique requirements, and this informs us that we're actually correct in how we design this. Each of these deserve to be separate entities. And the other thing around these entities is that if we apply our higher level bounded context, that of this is a native plant site, it informs us that considering these creatures pests is not correct. We should instead consider them wildlife. So this is because native wildlife is supposed to feed on these plants, and pest implies an irritant or something that doesn't belong. Subtle, but different. Next, let's look at vegetation. So I personally love potatoes, but it turns out potatoes aren't native to California, unfortunately. So goodbye. And our last user story might be that as a user, I should know where plants grow. And again, I might assume that these are different categories of places, like a parkway, a forest, a garden. But it turns out specifically they're interested in the latitude and the longitude of where these species are found in nature. So now we're getting somewhere. We've refined our user stories, we've extracted our entities, we've applied our bounded context, and we're left with what I think is a pretty good set of entities. So when should you use domain-driven design? Some pretty clear cases are that if your API serves multiple distinct clients, and this is because domain-driven design lets you map your entities by domains rather than by the clients. Another case is that if your organization has a strong product focus, then it might come more naturally to you to create these from these domain objects rather than work off of client or backend implementations. And domain-driven design has an added benefit that it's of more easily letting you define your entities up front. So it aligns very nicely with another concept called contract-driven development, which is just that, like define your constraints up front. And then using these practices lets you lets your schema happen up front, schema design happen up front, and then your client, backend, and other teams can all work simultaneously in parallel, so it's more efficient. And lastly, if your team has a history of creating ambiguous types or duplicating data in their schema, then you may benefit from adding a domain-driven design process to your development flow. So again, this could be as simple as a couple meetings discussing user stories together. And ultimately, again, like use whatever works best for you. Things can evolve, it's absolutely fine. And it might be even reasonable to use all three of these approaches or another approach that I didn't cover. But here are some recommendations for when to use them. And whatever you do, don't be afraid to make mistakes. Let your schema evolve, and be sure to tend to it from time to time. So with that, yeah, thank you for spending your time listening to me. It's been an honor, and if any of you want to talk plants or GraphQL or Hive, you can find me at the booth probably for the rest of the day. So thank you. And I feel like I talked really fast, so I assume I have time for questions. Does anybody have a question? Yeah.
Yeah, so in domain-driven design, you often have this context map.
Yeah.
Where you define relationships between different contexts.
Mm-hmm.
For example, open host or customer, supplier. How do you map this on a supergraph, let's say, these relationships?
Yeah, so if you're using federation, then that would be, so you see up here, this is exactly what you're talking about. Customer and product is defined both within these contexts. So you could easily map those as entities within federation, and then each of these sort of systems or the contexts provide whatever they need to provide, those attributes, those fields to those types.
But let's say the sales context has a relationship to the support context.
Mm-hmm.
But in GraphQL, you would rather have a client which does some queries or notations, but there is no real direct connection between the subgraphs. So, for example, if you need data from support context, would you also consider implementing this using GraphQL, or?
It sounds like a layer beyond potentially GraphQL. It sounds like you have one mutation that needs to touch multiple areas of your system. And yeah, I mean, you can represent your queries this way very nicely, but perhaps mutations is not so ideal. Hopefully that answered it. Any other questions? Cool. Thank you very much.